So yesterday we were talking about relating various expressions that we derived earlier relating to the rate of deformation of a small fluid element on one hand to the scalar components of the second order tensor, which is the velocity gradient tensor. This V is the Eulerian velocity field, and you take the gradient of that. We call it the velocity gradient tensor. You can also call it gradient of velocity tensor, but most of the times we call it velocity gradient tensor. In a frame fixed Cartesian coordinate system, if I choose that as my working coordinate system, then this would be the expression of the velocity gradient tensor. In index notation, this is what it is. If I insist on expanding and writing all the 9 components, or if I insist on writing the full expression of the velocity gradient tensor as sum of 9 terms, those would be the 9 terms. Okay. Now we define a new tensor, which is the symmetric part of the velocity gradient tensor. We give this symbol S underbar to it. This tensor is called the strain rate tensor. Strain, the word literal meaning of strain is something being stretched, compressed, right? The dictionary meaning has something to do with a distortion that is happening to something. And indeed, I'll show you on the next slide that all the rates of deformation that we defined and then derived expressions for, they will turn out to be the scalar components of this tensor S, and thus the name strain rate tensor is quite legitimate for this quantity. Keep in mind that strain rate tensor is a symmetric tensor, because any tensor which is born out of this kind of operation, a second order tensor added to the transpose of it divided by 2 is bound to be symmetric, and thus strain rate tensor is also symmetric. Also keep in mind that the strain rate tensor is also an Eulerian field. Velocity is an Eulerian field. You take gradient of that, this becomes an Eulerian field, and you take this symmetric part, that also is an Eulerian field. So at any location x, at time t you go, there are 9 components, scalar components of S you will find there. And those 9 components in general will be different if you go to another location, or even if you stay at the same location, you go to the next time instant, in general the 9 components will change. Physical meanings of the various components of S. So the way we have defined this tensor, S tensor, the way we have defined it here, if you work out the individual components of this tensor, S11 will be what? S11 will be this plus the same thing divided by 2. That will be S11. I mean, I'm talking only about the scalar components. S12 will be what? This plus this divided by 2. That will become S12, right? And similarly, other components can be written. So S11, as I said, is this. There is half there, but then del V1 del X1 is being added 2 times. So eventually it just becomes del V1 del X1. Does it have a physical meaning? Indeed. Rate of fractional change of edge length AB at time t. That's what we derived. Similarly, S22 will turn out to be Does it have a physical meaning? It has. What is the physical meaning, if I ask? Rate of fractional change? BC, no. Achha, you can say BC also, but I have been saying AD. But later we realized that AD and BC will have the same fractional change, right? So I will still write fractional change in AD, okay? This is just a revision. I have done it already many times. Fractional change in edge length of AD. Similarly, S33 will turn out to be simply del V3 del X3, and if I ask you to write the physical meaning of it, you should be able to write. Rate of fractional change in length AE. Okay. So the three components have clear physical meaning of the strain rate tensor. If you add all of them, if you add the 1, 1, 2, 2 and 3, 3 components, you get this. This also has a physical meaning. Remind ourselves, what is the physical meaning? Rate of fractional change in volume of the fluid element. Okay. Move on. Now I'm talking about S12. S12, according to the definition, mathematical definition of the strain rate tensor, it will turn out to be this. All right. Does it have a physical meaning? Does this have a physical meaning? This has a physical meaning, what I have circled here. What is the physical meaning of that? Rate at which edges AB and AD, their projections, the rate at which the projections of AB and AD on which plane? On which plane? No. AB and AD were in which plane originally? AB and AD, even E2 plane. Again, this figure is not very precise, but AB and AD, this is parallel to this, and this is parallel to this. 1-2 plane. So this quantity here is the rate at which the projections of AB and AD on even E2 plane were falling towards each other. Delta alpha plus delta beta, you remember? Limiting value, delta T. That's what it is. However, note that the strain rate S12 component has a factor of half there. Okay, has a factor of half there. So I mistakenly put 2 there. This is S12 is half the rate at which those two are falling towards each other. Does it have a physical meaning? It still has a physical meaning, but you have to keep that factor half there. Why is that factor half coming in strain rate component definition? Because it's the symmetric part of velocity gradient. 1/2 comes from there. But this thing has a physical meaning, and I just need to put a half there. Similarly, S23, according to the definition of strain rate, Am I right in saying that this was the rate at which they were falling? Was delta alpha plus delta beta by 2. Yeah, I think I'm right. S23 will by definition be, what will be S23 by definition? By definition, I mean this one. यहां से मैं बात करूं, ये definition है इसका. S23 क्या होगा? What will be S23? Right. Physical meaning, half rate at which projections, rate at which projections of something, projections of what? ADN, AB, AE, projections of AD and AE on which plane? E2, E3. S31, according to its mathematical definition, will be I'll leave this as a homework. I ask such questions on exam. I'll give you this and I'll ask you, give me the physical meaning in the sentence, long sentence. I'm leaving that for you. Okay. So it is the rate at which or projection of something on some plane collapsing towards each other. So I have given 6 physical meanings for 6 different components of strain rate tensors so far: S11, S22, S33, S12, S23, S31. But strain rate tensor has 9 components. Do I need to look for more physical meanings for the other components? No. Why? Because it's a symmetric tensor. So S12 is anyway S21, S23 is S32, and S13 is S31. Whatever physical meaning is there for S12, it is the same for S21. Now look at this situation from a different viewpoint. I have a strain rate, I have a tensor, second order tensor, strain rate tensor. It has 9 scalar components, symmetric, 6 independent scalar components. 3 of them have physical meaning which are associated with the rate of fractional change in length, whereas the other 3 have physical meaning which is rate at which angles are changing. See that? Same tensor, different components have different types of physical meaning. One is fractional change in length, the other is fractional rate at which angles collapse. That's fine. How about the SI units of all the components? Same, which is what? Per second. Now, when we talk about angles, you can say it is not per second, it is radian per second. That is fine. Radians we anyway don't count as a legitimate unit of its own. All right. As long as the angle is in radians per second, still specifies the rate at which angles change. All right. Such is the situation here. Okay. Now let's revisit the conditions under which a fluid element behaves like a rigid body. Yesterday I listed several conditions. There were 6 of them. I said that all 6 of them should simultaneously be satisfied for me to claim that this small fluid element is behaving like a rigid body. These are the 6 conditions. Based on completely physical interpretation. The edge length must not change. The angles which were 90 degree must remain 90 degree. This kind of requirement helped us identify these 6 conditions. Now note that these 6 conditions are all related to various scalar components of the strain rate tensor. This first condition, which I wrote as del V1 del X1 should be 0, means S11 is 0. Second one means S22 is 0. Third one means S33 is 0. And then these conditions, mind you, there was no half here. There was no half here. All right. But if this quantity has to be 0, it also means that 2 times S12 must be 0. Right? Which implies that S12 should be 0. So what I'm trying to say that these requirements, even though there is a difference of factor half, if we are hunting for conditions when these are 0, they actually mean that these strain components themselves are 0. Thus, I conclude in one single tensor equation, the conditions required for a fluid element to behave like a rigid body at a given instant is simply this. In a compact manner, the strain rate tensor must be 0. Does that justify the way we have named that tensor? Yes, as I said, strain means कुछ खींचतान हो रही है, right? कुछ distortion हो रही है. ये टेंसर वो टेंसर है जब वो 0 होता है तो वो खींचतान बंद, and you get a fluid element which is instantaneously behaving like a rigid body. All right. Okay. On problem set 3, yeah. No, strain rate is a measure of the rate at which a fluid element is behaving like a non-rigid body. Yeah. No, it's not for 0. 0 यहाँ हो गया. This I'm saying that thus strain rate is a measure, departure from the rigid behavior. I was saying in problem set 3, which will be uploaded probably at the end of this week, there will be a couple of problems in which I will give you a velocity field, Eulerian velocity field, and then I'll ask you to check whether some fluid elements are behaving like rigid bodies or not. All right. Normal strain rate and shear strain rate components. We classify those 9 scalar components of the strain rate into 2 groups. One group is called the normal strain rate component. The other group is called the shear strain rate components. What components belong to the normal strain rate component? These 3. When both the indices are same, or in other words, rate of fractional change in length, वो वाले components को हम normal strain rate components कहते हैं. Shear strain components are the other one. The meaning of the word shear is something like this. There are layers and you are trying to force one layer to move on the other. This action is represented by the English word shearing action. Any connection with that choice of the adjective and the physical meanings of these strain rate components? shearing, angle 90 degree, doing like this. Somebody is trying to make the upper face move more than the lower face. Kya hoga? Angles will tend. That kind of meaning is there in the background. Okay? Interpretation is there in the background. Later, we will learn that stress, which is also a second order tensor, we classify the components of stress tensor also as normal stress and shear stress. Okay. Will come later. For the time being, keep this in mind. This I have already said, SI units of all the components are the same, but physical meanings of individual components are different. Trace of a second order tensor. In some books, you will come across this word, trace of a second order tensor. If I have a second order tensor T, and if I have a frame fixed Cartesian coordinate system, I am expressing the tensor T as T11, E1, E1, etc. Then the sum of these three components is called the trace of the tensor. This is a mathematical definition, not only in fluid mechanics, but generally tensor. Symbolically, we will write this as trace of this tensor T is this. And if you want, you can use a more compact version, TKK, K being repeated. That's why it is the sum of three terms. Coming back to the strain rate tensor, trace of S will be this. Which turns out to be del Vi del Xi, right? Del V1 del X1, del V2 del X2, del V3 del X. So sometimes you will see in some textbooks, they will say that the trace of the strain rate tensor tells us the rate of fractional change in volume of the fluid element. Make sense? Trace का यही meaning है. I mean definition है वो, और right hand side का meaning है rate of fractional change in volume. You can also prove that SII, index notation implied. This is SI. You can prove that it is del dot V. What is del dot V? We have a name for del dot V. Huh? No. कल तो मैंने अभी तक बात ही नहीं की है इस क्लास में. I heard, yeah, divergence of velocity field. You go back and check. When del acts on a tensor with a dot product, we call that divergence of that tensor. This is divergence of velocity vector. You can show that SII is this. I leave this as homework. Further exercise on index notation. And thus, later somewhere, sometime in our course, we will also we will use this kind of equation. Trace of S is del dot V. Just an extra piece of information. So we talked about we defined this tensor, strain rate tensor. Now I'm going to define another tensor related to the velocity gradient field. We call it the rotation rate tensor. Symbol will be W. The rotation rate tensor. What is rotation rate tensor? Anti-symmetric part of the velocity gradient tensor. Okay. In a frame fixed Cartesian coordinate system, W will be Wij, Ei, Ej. It will be written like this. This is the sum of 9 terms. Since it is an anti-symmetric tensor, it will turn out W12 will be minus W21, W23 will be minus W32, and W31 will be minus W13. You can verify, it will turn out to be. And W11, W22 and W33 will be all 0. That happens for any antisymmetric tensor. Once you work it out, the scalar components, so see here, there are 3 components out of 9 scalar components, 3 are 0, right? And the other 6 are related to each other with a negative sign. All right, so non-trivial scalar components of W are actually only 3. With these 3, you get another 3 with minus sign, and the other 3 are 0. If you work it out, these are the components that you will get. You can see it, almost you can see it. यहाँ से 1 2 component निकालेंगे, that will be 1 2 will be del V2 del x1, इसका 1 2 component, और इसका 1 2 component will be del V1 del x2. दोनों को माइनस कर दिया, हाफ लगा दिया. These are the components split up. Any physical meaning of these? Recall these things. What are these things? ये symbol मैंने use किया है पहले. Average angular velocity vector. K components. Its components. Is there any relationship between omega 1, omega 2, omega 3 and W1, 2, 2, 3 and 3, 1? They are same. They are same. You can verify that this is what is omega 3, this is what is omega 1, and this is what is omega 2. Even the half factor was there. Remember, omega 3 में half factor था, and there was a reason why we put half factor there. कल पूछा था आपने, ठीक है? So sometimes the angular velocity vector is expressed not in terms of the components of angular velocity vectors are expressed in as the 3 components of the rotation rate tensor. We kind of use them interchangeably. You will either be told what are the scalar components of the rotation rate tensor, or you may be having access to information about the 3 components of the average angular velocity vector. They are the same. So in that way, rotation rate tensor has a physical meaning. Its components represent some average angular velocity vector components. Okay. At this point, I think it is relevant also to highlight a relationship between the components of this rotation rate tensor and a quantity, which is this. What is this quantity? This is called curl of vector A. I think this is the first time I am saying this in my class. You might have learned curl in some other course, or did I say? PY course, fine. Okay. So del cross A is called the curl of vector A, and for that matter, A can be any vector, mathematically speaking. Curl of vector. Here, right now in this class, in the context of fluid mechanics, we talk about curl of the Eulerian velocity field vector, del cross B. Now, if you work it out, I mean, if you try to express this vector, del cross B is also a vector. If you express this vector using a frame fixed Cartesian coordinate system, you will start with this step. You first write expression for del is here, and then you cross it with the vector v1, e1, v2, e2, v3, e3. Do all the steps, leaving it as a homework. You simplify, it will turn out to be what I have written here. 2 times W23 will be the even component of this curl of velocity vector. 2 times W31 will be the E2 component, and 2 times W12 will be the E3 component. Alternatively, it can also be written in terms of the components of the average angular velocity vector. 2 omega 1 E1, 2 omega 2 E2, 2 omega 3 E3. We have given this expression a lot of honor in fluid mechanics. We have given it a name, a very special name, the vorticity vector. Helps us understand more concepts about fluid mechanics, especially when the flow becomes turbulent. You might have heard this word. Towards the end of this class, I will explain what it means. But yes, for turbulent flows, lot of physics can be revealed by looking at this field, Eulerian field. Del cross B is also an Eulerian field. And since it gives us so much information, we have given it an honor and given it a special name, the vorticity vector. The symbol that we will use for vorticity vector is omega, small omega. You can see omega is simply 2 times, small omega is 2 times large omega. Vorticity vector is 2 times of the averaged angular velocity vector. So if omega turns out to be 0, if in some flow fields omega turns out to be 0, that also implies that big omega, small omega is 0, big omega is also 0. And if omega, small omega is not equal to 0, obviously big omega is not equal to 0. Since big omega gives us a sense of rotation of the fluid element, sense of rotation in an average sense, if this large omega or small omega if either of this is found to be 0 over the entire flow field, that flow field is called irrotational flow field. Irrotational flow field. What it means is that no fluid element in the domain is having any sense of rotation. Irrotational. In real life, we don't come across such flow fields very often, which are irrotational, but it has a theoretical importance, and we will discuss that in class. We will look at this class of flow, which is called irrotational flow, and we will try to learn some physics from it later. But at that time, either we will say that big omega is 0, or we will just simply say vorticity is 0, and thus the flow field is irrotational. So that interchangeability is coming because of this relationship, that there is just a factor of 2 which makes them different. These points I have already mentioned earlier, but let me emphasize once again. Velocity gradient tensor, strain rate, rotation rate, they're all Eulerian fields and all have SI units per second. So far, we have expressed all these in a frame fixed Cartesian coordinate system. But then tensors, once you start talking about the tensors themselves are invariant to the choice of coordinate system by very definition, right? So S tensor, if I talk about the S tensor, of course, in the frame fixed Cartesian coordinate system, it will look something like this. I have not written everything, but I hope you follow what I mean to write here. It will look like that. But suppose because of some reason I have been forced, or I choose myself to express this tensor, same flow field in cylindrical polar coordinate system. How will I write that tensor? To begin with, I will have something like this, and then what should I write? Let's use theta. ठीक है, S R, ठीक है, E theta ER or ER E theta. Eventually, it will not matter because it's a symmetric tensor, but let's be meticulous about it right now. ER E theta, right? Because R is coming first. Then del अभी कहीं नहीं है, S SRZ, right? And then you will have theta r, right? And then I'll leave some blanks for you to fill. I'll just ask you what's the last component. 9 of them. क्या होगा last वाला? SZZ, EZEZ. Okay. Same flow at this location at this time. S is a tensor. You choose a Cartesian coordinate system. You write it like this. You change your coordinate system and don't change anything else. With new coordinate system, you will have to write it like this. And then we know that SRR is not the same as S11 in general. Even for two Cartesian coordinate systems, S11 of one coordinate system will not be the same as 11 of two other, right? So definitely SRR and S11 are not the same. But when you put all together, it becomes S. When you put all this together, it becomes the same S. I have the full expression here. Now this representation is just using SRR, SR theta. It's very symbolic. But if I insist on finding what these are actually, what these are, I mean, what is SR, what is SR theta, in terms of what? In terms of velocity field. I should be able to write. That will require some derivation. So first you will have to write S as what I have here, which again is a coordinate system independent relationship, holds good for all coordinate systems. And then problem set 1, question number 3, we know that del is this in cylindrical polar, and V will be expressed like this in cylindrical polar coordinate system. And then you go ahead and find del V in cylindrical polar coordinate system. PS1 type approach. This particular question I did not put, but I encourage you to do this as homework, practice. Find del V. And then once you have del V, you find del V transpose. That's easy, just to swap some scalar components. And then you assemble together this in cylindrical polar coordinate system. That's the approach. You will get something like this. Some components I have put there, some components I have left as homework. Please do this. SRR will turn out to be del VR del R. That sounds simple. But look at SR theta. So many things are there. And then SRZ is also simple, more like Cartesian coordinate system. But some other components are more complicated. I say some of the things I have left, but have I really left those things? What do you think? Yeah, since it is symmetric, I have actually written everything there. Just you have to copy and paste things here. So the full answer is there. Please make sure you get the right answer. Please make sure you are able to get the right answer process wise. Okay. Fine. Now let's talk a little bit more about the physical meanings of strain rate components now in cylindrical polar coordinate system. Now to visualize the physical meanings of these components, which components? SRR, SR theta, SRZ. In cylindrical polar coordinate system, we need to imagine a fluid element of shape appropriate to cylindrical polar coordinate system. If the working coordinate system is a Cartesian coordinate system, the shape of the fluid element that you take at time t0 is a cuboid. And then you talk about AB, AD, AE, their projections on 1, 2, 2, 3, 3, 1 plane. When you are working with cylindrical polar coordinate system, you have to do justice to the shape of the fluid element that you are taking. The fluid element of a cylindrical polar coordinate system should be like this. This is the shape of the small fluid element that you should take to interpret the physical meanings of these things. I hope you are able to visualize the shape of the fluid element. Kya hai shape? Vertex A or the fluid particle at A is here. I go radially out by delta R. This is the picture at T0 or T, not T0, at time T. You go radially out, radially away from the axis. Delta R, you have B there. And then you go delta theta along the direction of E theta. Okay. And you go delta Z along the direction of EZ, written here. So you get a kind of curved shape of the fluid element. Are you able to visualize this? Okay. Now, with that fluid element in front of you, we can interpret the physical meanings of various things. For example, SRR is the rate of fractional change in edge AB. SRR is this. S theta theta will be the rate of fractional change in which length? I have not written here, but I am asking this question. S theta theta, what will be the physical meaning? Make an English sentence for me. Rate of fractional change in edge, itna to hoga hi. There is no doubt about it. All normal strain rate components will be rate of fractional change in edges. But which edges, that you have to identify for me looking at that figure. S theta theta, rate of fractional change in which length edge? You can say EH or you can say AD. Same. All right. SZZ. SZZ कौन सा है? Rate of fractional change of edge तो है ही. Which edge? That is the only A. Very good. Then we come to SR theta. SR theta will again be rate of collapse of some edges because it's a shear strain rate component. All right. But which component? Which projections on which plane? First of all, there is a factor 2. You either say 2 times SR theta is something physical, or you say SR theta is half of something physical. That factor will have to be there. And then please complete the sentence. I have not completed, or maybe I have. Rate at which projections of AB and AD on ERE theta plane are collapsing towards each other. On ERE theta plane. Where is ERE theta plane? This kind of horizontal plane in this figure. Right? AB ऐसे है, AD ऐसे है, ये horizontal plane पे इनका projection, इन दोनों का projection, what rate they are collapsing towards each other. That's what is 2 times SR theta. And then I have left other things for you, and I will ask some questions later. I hope you were able to answer. Let's do this exercise verbally. 2 S theta Z is what? Somebody please repeat a sentence for me. S theta Z is half the rate. I start the sentence. Half the rate. Aage bolo please. AD and AE on which plane? E theta and EZ plane are collapsing towards each other. Very good. Thank you. Similarly, baki teesra component B, you should be able to make a sentence from that. And then the fractional rate of fractional change in the volume of this fluid element will be represented by del dot V in coordinate system independent form. But if you want the exact expression of del dot V, you will have to work on the various things here. I mean, del V and all that. This is again in PS2. Please check. Sorry, PS1. I think problem question number 4. I have asked you to express del dot V in cylindrical polar coordinate system. So that will give you the rate of fractional change in volume. All right. I take a pause and I want to check how we are doing as far as the topics are concerned in this course. This is a part of the course document I shared with you, and it is on Moodle right now. Tensors we have completed. Particle and rigid body mechanics brief review we have completed. Description of fluid motion completed. What topics we covered under this heading? Molecular description, continuum description, within continuum, Lagrangian, Eulerian, all that was here. Fluid kinematics. Fluid kinematics is essentially this rate of deformation and angular velocity, etc. that we have covered. All right. So we are here. Next topic is governing equation of fluid motion. I'll take a couple of minutes and then I'll let you go. Governing equations of fluid motion. What I mean by governing equations of fluid motion is basically the equations which can be solved, or which must be solved rather, the equations that must be solved to get these variable fields. So far I told you that the velocity field is V, and then I kept writing the spatial gradients and I kept interpreting the physical importance. But who gives us this velocity? One student asked this question. I think Aryan asked me this question. How do we get the velocity? At this point, just for exercise problem sets, I have been making up velocity fields. और ऐसे ही दे दिया, इससे कुछ निकालो, ये करो, वो करो. But a real flow field with its boundary conditions and initial conditions, I can't make it up. It has to be solved for. When I say it has to be solved for, I need governing equations. Those are the governing equations that we will derive in this course. Now, what do you think those governing equations would depend on, or how do we get those governing equations? Based on what? Any guess? Any guess? Go back to APL 100. I wanted to find the velocity acceleration of a fluid particle, a particle. Okay, you were solving some equations, right? F equals ma. You were solving. What law is that? Newton's second law or Euler's axiom? That we will recall. Fluids को भी follow करना है वो. Euler's axioms. Any other thing do you think will be of relevance? Any other law जो आपको पता है? Conservation of mass. We will have to invoke. इसके बाद बताओ, एक और बच जाता है. You have learned this many times in school. Mass, momentum, energy. क्या कहते हैं उसको? एनर्जी वाला जो लॉ है. और जनरल नाम बताओ. नहीं. लॉ ऑफ थर्मोडायनेमिक्स, ऐसा ही कुछ कहते हैं ना. थर्मोडायनेमिक्स, फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स. वही 3 इक्वेशंस यहाँ भी यूज होने वाले. Based on that, we will derive the governing equations of all these quantities. Okay, we will do that on Friday. Start that on Friday. We stop here.